very helpful. Our next speaker is Dmitry Pekurovsky from PSC. So Dmitry's going to talk about some work he's done with Fast Fourier Transforms, 3D Fast Fourier Transforms. And this work has been ongoing for several years, and he ended up developing, a downloadable standalone package that anyone can use. And I know that I've heard this, really favorably spoken about at different reviews that I've been on over the years when people have reviewed the program and they've heard about this code and say, wow, boy, that's really a tremendous accomplishment. That's really something that's going to be generally very useful. And so I look forward to hearing more about it here today. So Dmitry, I can see your slides just fine. You can go ahead and make them full screen. And this is work with a number of different PIs, but I think it first started with P.K. Young at Georgia Tech. Runs at several sites in Excel, one of the larger. So go ahead and take it away, Dmitry. Hang on, I'm going to mute everybody else.
Presentation mode is now enabled.
Okay, go ahead, please.
Hi. So as Nancy said, I will talk about this package that I have created that does scalable Fourier transforms. And as Nancy mentioned, this has originally started as a collaboration and advanced user support. And then I just thought, why not generalize it and make it available to other users? Because Fast Fourier Transforms is very commonly used in many areas. It is computationally demanding algorithm. It's not a cache-friendly algorithm, so it stresses memory bandwidth. And parallel implementation is very communication intense. So, of course, there are many libraries that provide Fourier transforms. However, when you talk about scaling to machines like petascale size machines and beyond, there are actually some limitations on the scaling of most of these libraries, and that's the motivation for this work. Just a few general remarks about Fast Fourier Transforms. Basically, it's in 3 dimensions. I'm going to talk about 3-dimensional Fast Fourier Transforms. So basically, you need to apply 1D Fourier Transforms in each of the 3 dimensions in turn. And most implementations use so-called a transpose approach. So you apply.
Dmitry, can you hang on for just 1 second? I know that I've heard that TAC can't see the slides. Hang on, let me.
Presentation mode is now disabled.
Is there anyone else on the call who cannot see the slides? I can see them. Okay, I'm not sure what the problem is, TAC folks, but it sounds like it's not a general problem. I'm sorry, I'll have to let Dmitry go on here.
Presentation mode is now enabled.
Okay. Go ahead, Dmitry. I think they're set, actually. Okay.
Okay. So the approach is that we transpose the data so that the data is local in the direction that we are doing the Fourier transform. So basically, we can consider one-dimensional decomposition where each processor is responsible for a slab of data or several planes of data of the cube, or 2-dimensional decomposition where each processor is responsible for a column or a pencil of data. And of course, the 1-dimensional decomposition suffers from a severe limitation in concurrency. Because concurrency is limited to n, the number of grid points in 1 dimension. And so it's not enough parallelism to run on tens and hundreds of thousands of cores. Unfortunately, this is the approach that most widely available libraries to date have been using, such as FFTW, PESSL, and many others. To overcome this limitation, we're going to talk about 2-dimensional decomposition, where concurrency is limited now by n squared. So, in theory, scaling to much larger core counts as possible. Briefly, this is the algorithm. So, each processor is responsible for a column. In this example, you have 16 course or tasks. We start with performing 1D FFT in X dimension that is local. Then we change the data, transpose the data, so that, rearrange it so that now it's local in Y dimension, and then we can do FFT in Y dimension, and then transpose again to arrange it so that Z dimension is local, and do FFT in Z dimension. So there are two all-to-all transposes in this algorithm. So P3DFFT is an open source library. It is available on this website. It implements 2D decomposition. Of course, 1D decomposition is an option. It features right now. It features real to complex and complex to real 3D transforms. Also, currently it features Chebyshev transforms in one dimension. It has Fortran and C interfaces, single double precision. It can handle uneven cases of array dimensions. It can do either in place or out place. The web page has the package has many examples in both C and Fortran, and a performance optimization is a big factor in designing this library. Just very briefly, I'll touch on the implementation. It's implemented in Fortran 90 with MPI. It calls FFTW or ECSS to compute 1D FFT. The transpose is implemented in 2D decomposition by setting up 2D Cartesian sum communicators. And as I mentioned, two transposes are needed. Each transpose is an all-to-all operation, but one is done in rows and the other one is done in column communicators. Typically, a large portion of total time, to 80% or so, is spent in communication. It's very communication-intensive code. I'm talking about large-scale runs. It's highly dependent on optimal implementation of MPI all-to-all, which varies from vendor to vendor. And performance can be sensitive to the choice of processor grid. I mentioned that there are two-dimensional Cartesian grid that we are setting up. So depending on how you do it, get somewhat different performance. As this diagram shows, performance on Kraken and Ranger, and there is a significant variation in performance depending on the shape of the processor grid. Just a few general remarks about scaling all-to-all communication. The performance is directly affected by bisection bandwidth of the interconnect. Increasing the number of cores decreases the buffer size proportionately. So if you have scalable bisection bandwidths, actually you can, in theory, get a perfect scaling. Of course, there are many other factors. There is contention on the network and many other factors that interfere with that. But I'm talking about the upper limit. On torus topology, such as Cray XT, for example, the bisection bandwidth scaling as p to the power of 2/3. So the best we can ever hope to get is the inverse of that in terms of scaling. Well, what about process mapping? I've tried to experiment with process mapping a little bit, and I have not seen a benefit so far. Basically, we have all-to-all pattern. It's very hard to rearrange things and make it better somehow. That's all I can say in the few minutes that I have. Let me show you some results from strong scaling on Cray XT5, a Kraken machine. What's shown here is these lines showing results of timing results from a simple test routine that basically does a Fourier transform, three-dimensional Fourier transform, once forward and once back. And the size here is 4096 cube transform. So these numbers here show the best processor grid shape. The upper line, the main result here is the red line here in the middle. That's the main result of performance. The upper line here is a little higher. Is a version implemented was MPI all-to-all V, which I don't have time to go into detail, but for technical reasons, it seems to work a little bit worse than MPI all-to-all. Also, I did a fit to the communication time here based on the expected scaling, as I mentioned, p to the power minus 2/3, and I see that it matches the data pretty well here. And this light blue line shows the flops, the teraflops to be precise. So this is the strong scaling. Here's weak scaling. We go from here on the x-axis to show the linear grid size. So we go from 512 cubed to 8,000 cubed grid, and we're going from 16 cores to 64K cores. This is on Kraken again. So every time we double the grid size, we increase the core count by 8 times because it's a three-dimensional problem. So, of course, if it was perfect scaling, we would expect a flat line. This line is not flat. On the other hand, we should keep in mind that the ideal scaling is on torus networks. Again, is limited by p to the power of minus 2/3. And so, considering that, this is actually not bad results. And here's plots comparing one-dimensional versus two-dimensional decomposition. Although one-dimensional decomposition wins a little bit on lower co-counts, in this case, this data is for 2048 cube grid. But you can see that it can only go as far as 2048 cores. It just does not scale any further. Two-dimensional decomposition can scale further. The applications of P3DFFT the library has been already applied in a number of codes. Some in Exceed, and some more generally in areas such as turbulence, astrophysics, oceanography, material science, and several others. Let me talk about one particular project. This is the original project that that started it all. It's DNS turbulence code from Georgia Tech with the author of that code is P.K. Young. It simulates isotropic turbulence on a cubic periodic domain. Turbulence is characterized by disorderly nonlinear fluctuations and spans a wide range of interacting scales. DNS, dynamic numerical simulations, is an important tool to understand turbulence. In the algorithm, this code uses a pseudo-spectral algorithm to solve the Navier-Stokes equations. And in this algorithm, three-dimensional Fourier transforms is a crucial part, and it's in fact the most time-consuming part. Two-dimensional decomposition has been applied to make this code scalable. And here are some results for 4K cubed and 8K cubed grids. This is on Jaguar. These lines show the perfect scaling lines. The blue symbols show performance of code with scalars on top of velocity fields, and the red lines is just velocity field. In terms of ongoing work, there is quite a number of things that I'm still working on for this library. Part one is expanding flexibility and improving interface. expanding the memory layout options, adding different types of transforms. For example, recently added the Chebyshev transform, adding the ability to isolate transposes. So the goal is to make it more general, so that the user can apply this to other transforms, similar transforms, not necessarily Fourier transforms, but ones that require locality of data. And on the other hand, I'm working on performance improvement, finding ways, because communication is a very expensive, very big part of the penalty here, bottleneck. So I'm exploring ways to optimize it, and in particular to implement communication computation overlap. There's a number of approaches there. We can use MPI2 or OpenMP or Coarse-grain Fortran. Also, I am experimenting with a hybrid MPI OpenMP implementation. I have some results, some preliminary results. I don't have time to go into more detail here. These are results of hybrid MPI OpenMP on Kraken. You can see that two threads runs with two threads perform better than with one thread. So there is some advantage in using threads. However, this is a very kind of it's not a generalized result. This is particular to this problem and this platform. In other cases, I have seen that actually pure MPI is better than hybrid. So to conclude, there's a 3DFFT library that's available. It's an open source. We see pretty strong performance. It has been applied in a number of users' codes. The work is ongoing to expand the options as well as expand the performance. This is an example of a project that came out of our Integrated Advanced User Support collaboration. Now benefiting wider community, and I believe this will be also a future Exceed community code. This is also the 3DFFTs are also an excellent testing tool for future platforms capabilities, because it stresses bisection bandits, stresses MPI implementation, and you can see how efficient these are one-sided protocols. So that's all I have. Thank you very much.
Dmitry, thank you very much for an excellent talk. Let me go ahead and unmute the phone line here.
Presentation mode is now disabled.
I had a couple of questions that I was writing down as you were speaking, but you answered most of them by the end of the talk. So, do you find that people are interested in the code primarily because it allows them to scale to higher processor counts, so they're looking at a problem in more fine-grained detail rather than just speeding up a given problem, or is it a little bit of both?
Well, it's hard to say. I think it's a little bit of both. But for example, in the case of turbulence, one needs to resolve smaller scales, but at the same time keep the box side of the box the same. So yes, you do need to go finer and finer, and it's crucial to go finer and finer.
Yeah, I think this is such a terrific example of really generalizing an approach in a completely downloadable way for others. I mean, not all our ECSS projects lend themselves as well to this, but I think it's really nice that you took the extra initiative to really package this up. Probably, no one was pressing you to do this as part of the project. You answered some of my questions with the number of download statistics and what other kinds of domains were using the code. I know there are a few other ECSS projects in the pipeline, I think, waiting for your expertise to help them. People have been standing in line a bit for this capability. And as you mentioned, we're looking at making this available on all the Exceed platforms as a community code. I don't know if John Kaz is on the line there. I guess he probably couldn't see the wide, so he's probably at a slight disadvantage there. Any other questions for Dimitri from folks on the line here? Okay.
I had a question. This is Darren Adams at NTSA again. I was wondering about your hybrid OpenMP, and I'm assuming that's just for the FFTs that you're doing the hybrid, or that you're doing the OpenMP parallelization?
Yes.
Okay.
For FFT.
And are you actually using FFTW's OpenMP capability, or are you doing it above FFTW?
I'm not using FFTW's capability. I'm just parallelizing it myself.
Okay. Yeah. Okay. Because I've had a similar problem, and I think I had good luck doing was doing a series of 1D FFT, so I just did a parallel loop, basically, and got pretty good results. Okay.
Yeah.
Okay, with that, I think that wraps up another symposium. I want to thank our speakers, especially for a few excellent talks that I think will be viewed later because of the general nature of them. Next month, we're going to take off because of the Exceed 12 conference. So I hope to see many of you there, and then we'll pick up again in August. So thank you very much, everyone, for joining.